Good evening, sir.
Good evening, sir.
Right.
Good evening, sir.
Good evening, people. Good evening. Good evening, everyone. Just a minute. So,
Sorry,
you guys have,
हाँ.
yes, please ask.
सर हमने कल सेकंड थ्योरम में लिखा था कि if the potential at some point is infinite, the wave function vanishes or does not exist. Okay, so my doubt is that is it at that point या उसके बाद wave function
From that point onwards,
wave function exist नहीं करेगा.
हाँ मतलब अगर x equals to 0 पे infinity है, wave function will be infinite at x equals to 0. It cannot exist.
उसके बाद x equals 0 के बाद wave function exist नहीं करेगा.
Including x equals to 0.
Okay, sir.
ठीक है. Basically equality matters. In fact, like just like you pointed this out, I was about to stress on this topic when I was teaching you free particle that equality matters. But yes, okay. Now just a second. I got late with the daily chores. Okay, so I think we have written. We have started with applications of Schrodinger equation, and we have written 4 theorems so far. And the fourth theorem was any linear combination of degenerate wave functions is also eigenfunction belonging to the same eigenvalue. Right? Do you have any questions until here? Then please ask me right now. I'm assuming it's all good then so far. Chalo, let's continue, people. Now let's learn the fifth theorem, people. Okay, so if potential, just a second. V of x is symmetric. Okay, what is the meaning of symmetric? Basically, even function, people. V of x will be equals to V of minus x. If something like this happens, then wave function is either symmetric or antisymmetric. It's either symmetric or antisymmetric. But it will be either of them for sure. It will be just not a normal wave function. It will be either symmetric or antisymmetric. I hope you realize that there is a difference between a function which is not symmetric and a function which is antisymmetric. Not symmetric and antisymmetric are not the same thing, people. English matters. Like when you say even function and odd function, so when you say the function is not even, that does not mean it is odd. And when you say that the function is not odd, that does not mean it is even. Okay? Even is a special function, odd is a special function. Not being even does not necessarily mean it's odd. For example, suppose if I give you that there is a wave function, let's say x squared. Okay, replace x with minus x. Replace x with minus x. Okay, so this is minus x squared, which again becomes x squared. Okay, so as you clearly see, the value of psi of x, and when you replace x with minus x, both of them share the same value. When this happens, you call them even. Absolutely. Okay. Now suppose if I give you psi of x is x cubed, replace x with minus x. So if you replace x with minus x cubed plus minus of x cubed. But who is x cubed? X cubed is psi of x. X cubed is psi of x. So minus of x cubed is actually psi of x. So basically we are getting psi of minus x is negative of psi of x. When this happens, when psi of minus x is negative of psi of x, you call it odd. So when psi of minus x and psi of x are equal, that's even. When psi of minus x is negative of psi of x, that's odd. But when neither of them is happening, it is neither even nor odd people. So like for example, if I would give you, let's say, psi of x is suppose x minus 2. Okay, replace x with minus x. What are you going to get? Replace x with minus x. So we will get minus x minus 2 because there is no relationship between them actually. Like no relationship. Psi of x and psi of minus x, there is no linear dependence on them. It's x minus 1, this is minus x minus 2. Even putting minus common, you get x plus 2, because you have x minus 2. No relationship whatsoever. So this is not even. This is not even odd people. Neither even nor odd. So when you say a function is even, it's even. But when you say a function is not even, that does not mean it has to be odd. Like it could be something like this also. It is neither even nor odd. People usually think that symmetric, it has opposite antisymmetric, but antisymmetric they think that it means it is not symmetric. No, people. This can be called as symmetric. Even function means symmetric. Okay. Odd functions means it means antisymmetric. But when you say it is not symmetric, or when you say it is not antisymmetric, it could be something like this, where it is following neither of the property. This is neither symmetric nor antisymmetric. This is neither symmetric nor antisymmetric. No relationship whatsoever. Okay. So first to make a note of this, before we start with theorem 5, I want you to make a note of this first, with clarity.
Sir, antisymmetric and symmetric.
Pardon?
Sir, antisymmetric and skew symmetric is same.
Hi, it's anti and skew are same. That's fine. Skew symmetric and antisymmetric. That's it. Okay. Your voice is breaking completely. Humna, your voice is breaking. No, I cannot hear you. It's completely breaking.
Sir?
Huh? Hello. Yes. Previous slide. Okay. No, anyway, I'm coming to this. You don't have to write this. First, you write the note. Then we'll go to theorem 5. First, I want you to move this. After this, we'll go back to theorem 5. Have you copied this, people?
Yes, sir.
Okay. Others also, if anybody is writing this note, let me know. Okay. 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 So now you can write theorem 5. Okay. Now we can write theorem 5. So if potential V of x is symmetric, then wave function is either symmetric or antisymmetric. Basically, it has to be either of them. Now, you can never say that it is neither symmetric nor antisymmetric. It has to be either symmetric or antisymmetric. It cannot be a normal function. It has to be linearly dependent function kind of stuff. You can say psi of x and psi of minus x must have a relationship. The meaning of this is that psi of minus x and psi of x must have a parity operator between them. They must have a relationship between them. Psi of minus x and psi of x must have a relation. Okay. You can say linearly dependent relation. Must have a linearly dependent relation. Given by. Okay, so I will teach you something. I'm not sure. Have you learned parity operator by any chance? In my classes? No. Okay. So psi of minus x and psi of x must have a linearly dependent relation given by parity operator. Let's learn this. No problem. So see, when I say psi of minus x, Your voice is breaking.
Clear.
Again, your voice is also breaking. Is it a problem from my end?
No,
No, sir, your voice is totally clear.
Okay. I mean, yours, even when they are asking, you are not able to hear properly.
Yes, sir, also.
Yes, sir.
Right. Okay. So psi of minus x, when you say it has a relationship with psi of x, what kind of relationship? Like when you write alpha. So alpha could be anything, 2, 5, 10, 15, but no, we don't want that. We want either it is 1 of psi of minus x or we want minus 1 of psi of x. We want either of them. Okay. So basically that operator, the operator which will be either +1 or -1, that is known as parity operator. Basically. Okay. So you can write when you okay. So they have a relationship between them given by parity operator. It's like, so when you apply, let me think of it this way. Hang on. I will write lambda here such that if lambda is +1, you call it even parity. You call it even parity. And if lambda is -1, you call it odd parity. That's it. Okay. Because if lambda is 1, what happens? Psi of minus x will be equal to psi of x. So that's symmetric wave function even. F of minus x is f of x. That's even function equal. And if psi of minus x is negative of psi of x, that's odd function and is symmetric wave function. Okay. So here you have even parity, here you have odd parity. Just make a note. Copy people. Sure. Next. So again, to explain you, people, the even parity operator is written as p plus cap usually, and odd parity operator is written as p minus cap. Okay. So for an example, if suppose you take derivative of e raised to x, this is e raised to x, huh? Derivative of e raised to x is e raised to x. So I can also say this is basically when you apply operator on derivative of e raised to x, I got 1 here. That 1 can be written as p plus cap. This is known as even parity. So when you apply even parity on e raised to x, you get the same function back. Okay. So I'll write it this way maybe here. So when you apply even parity on a function, you get the same function back along with this decimal 1. You get the same function back with let's say eigenvalue 1. But when you apply odd parity, on a function, you get -1 into f of x. You get -1 into f of x. So like I said, derivative of e raised to x is e raised to x, or you can write it as 1 into e raised to x. 1 into e raised to x can be written as basically p plus cap into e raised to x. So d by dx is an even parity operator. Understood? Here d by dx is even parity operator. But if suppose you had an example, derivative of e raised to minus x. So now what is derivative of this minus e raised to minus x? You can write this as -1 e raised to minus x. I can write -1 e raised to minus x as p minus cap e raised to minus x. So you can say that here d by dx is odd parity operator. Okay, take a look. Here d by dx is odd parity operator. This is in the subscript now, p plus and p minus. Plus and minus are in the subscript. So +1 is basically like when you apply even parity on function, you get same function with eigenvalue 1. When you apply odd parity on function, you get same function with eigenvalue -1. Here, tell me if you have any questions. This was a small diversion. I did not plan to teach you parity operator, but it's okay. Please ask me if you have any questions. Don't hesitate. Shall we? Let me
Just a minute.
take your time. So apply parity operator on a function, you will get +or -1 into the function. Simple. In general, you can say applying parity operator on a function, you get +or -1 into the function. +1 means it's even parity operator, -1 means it's odd parity operator. Plus.
Yes, sir.
Yeah. Sure. Others also please let me try it out. Next. So in order to understand the statement, obviously, so far people have literally understood all the theorems, all the postulates everywhere, and not just asked you to by heart, teacher, chalo by heart karo, assume karo, let. No. We have literally ensured that you understand the meaning and significance of each theorem. So this also I'm not going to allow you to just by heart that sir v of x is v of minus x by heart every function is either symmetrical or asymmetrical. Now, let's understand why it is symmetrical and asymmetrical. Okay? Why it should be symmetrical and asymmetrical. Let's understand. Okay. So now we are just going to explore the theorem more deeply. Okay? I have to work hard for that, but it's worth it, completely worth it. Just a second. Okay. So we are just exploring statement number 5, theorem number 5. So people, it is given in the question that potential is symmetric. As far as potential is symmetric, wave function must be symmetric or antisymmetric. It cannot be a general random wave function. It cannot be that. Okay. People, what is Schrödinger equation? Let's try Schrödinger equation. Minus h square upon 2m. Okay. D square upon dx square plus v of x into psi plus v of x into psi. This is E psi. Okay. Let's say this is our equation 1. Now replace x with minus x everywhere. People. Replace x with minus x. So what do we get? Minus h square upon 2m. D square upon d minus x the whole square. That's dx square. Okay. Plus v of minus x. Here I have got psi of minus x. This is E into psi of minus x. Okay. Next. But they have clearly mentioned that this v of minus x and v of x are equal. It's symmetric, people. Okay. So here now I can replace v of minus x is actually v of x. Copy this much first. What happened? So now we have replaced x with minus x. Here also remember x is replaced with minus x, but then it becomes square now. So it becomes dx square. Okay. So we have minus x square upon 2m, d square upon dx square plus v of minus x is v of x. So the operator goes back to the original operator into psi of minus x. Into psi of minus x is e into psi of minus x. Is e into psi of minus x. What do we see from equation 1 and equation 2, people? Operator is same operator, same operator. Here also you have exactly same, and here also you have exactly same operator. Here you have the same eigenvalue, people. But the wave functions are different. Okay, so yesterday we had learned people that if we have got two wave functions, which share the same eigenvalue, then you call them degenerate wave functions. So first of all, we can write here psi of x and psi of minus x are like they share the same eigenvalue. E. So they share same eigenvalue E, and we can say that. So these are nothing but you can say degenerate wave functions. These are degenerate wave functions.
So psi of x and psi of minus x is linearly independent.
No, when you say hi, so these are right now linearly independent, but they could be linearly dependent also.
But we
Okay,
strictly
so
have that condition.
let's not try this right now. But first, right, they share the same eigenvalue. Right? They share the same eigenvalue. So we don't know, obviously we don't know whether they are linearly dependent or independent. Yesterday I had taught you that same eigenvalue can be shared by infinite numbers of wave function, but those infinite are actually linearly dependent on some specific values, and those are linearly independent. So we don't know right now, obviously, whether psi of x and psi of minus x are dependent or independent, but they share the same eigenvalues. People, I remind you, yesterday we had learned that phi1 was a function, phi2 was a function. They shared the same eigenvalue, E. Okay, and we had also learned the linear combination also shares the same eigenvalue. That was the third theorem. The linear combination also shares the same eigenvalue. So that is where you say that the other wave functions are linearly dependent on that. Okay, but even they share the same eigenvalue. So how will we know whether these were dependent on each other or independent on each other? We don't know that. So we will take both the cases. Yeah, you can right now we don't know whether they are linearly dependent or independent. Right now we don't know that they are linearly dependent or linearly independent. Both are possible. Absolutely, both are possible. Okay. So let's take the first case where they are linearly dependent on each other. I hope you have copied. Tell me if I have right. Case 1. Let us say that psi of x and psi of minus x are linearly dependent on each other. Remember, in that case, infinitely many combinations are possible. Yesterday we had learned if suppose one of them is independent, suppose phi1 was independent, phi2 was independent, then linear combination of them can give you another eigenfunction which also shares the same eigenvalue. But that way you can have so many combinations, alpha phi1 plus beta phi2, but alpha and beta can take infinite values. However, we don't care about the dependent wave functions, we only care about independent functions. But obviously, how will I know right now whether psi of x and psi of minus x are independent or not? I don't know that at all. Okay, so right now we are taking a case where they are dependent on each other. But in that case, there can be infinitely many values. So psi of minus x, suppose it is a times psi of x, they are linearly dependent on each other, but a can be anything, whatever you want. And people, if a can be anything in this, then it's simple. If a is plus 1, psi of minus x will be equals to psi of x. You got symmetric wave function. If a is minus 1, psi of minus x is equals to minus of psi of x, you got anti-symmetric wave function. Okay. So when potential is symmetric, psi of x and psi of minus x share the same eigenvalue. We don't know whether they are dependent or independent. So if they are dependent, then there are infinitely many combinations possible. Out of those infinitely many combinations, one combination is symmetric, one combination is anti-symmetric. Copy this, and then we will also see what happens if it is independent. Copy this.
So in this case, we are ignoring those cases which are neither or not even, right? Because we can be anything.
Oh, yes, absolutely.
We are ignoring it.
Yes, absolutely. No?
Yes, sir.
Okay, let's take case 2. Now, obviously, now the question is, sir, what if they are linearly independent? Suppose they are linearly independent. Okay, then it's okay. Then in that case, linear combination of them, people, linear combination of them also shares the same eigenvalue. We know that. Okay, no problem. Linear combination of them must share the same eigenvalue. Okay, basically these two are right now, since they're linearly independent, you can say twofold degeneracy. Like I taught you this yesterday. If you have 3 linearly independent wave functions, it's threefold degeneracy. All the other wave functions are linear combination of them. Okay, so right now if you say they are linearly independent, but they're anyway sharing the same eigenvalue. They are anyway sharing the same eigenvalue. So you can say it's twofold degeneracy because they share same eigenvalue. But the best part is the linear combination also shares the same eigenvalue. Okay, okay. So let's define a function once again. A function where this is alpha psi of x plus beta psi of minus x. Okay, and define the function. Linear combination, this also shares the same eigenvalue. Alpha psi of x plus beta psi of minus x. Okay. Now in this, let's take case 2a. People, again, you can give infinitely many values to alpha and beta, whatever you want. Again, we will take a case. Suppose alpha is 1, beta is 1. What happens to f of x? F of x is psi of x plus psi of minus x. Okay. Now replace x with minus x. What happens? F of minus x. This is psi of minus x plus psi of, if x becomes minus x, then minus x will become x. People, a plus b or b plus a, that is fine. So if I write psi minus x plus psi x, or if I write psi x plus psi minus x, that's fine. But who is psi x plus psi minus x? That's f of x, people. What did you get? You got f of minus x is equal to f of x, which is this symmetric wave function. So even otherwise, people, the point was basically, if potential v of x is symmetric, people, we can always find wave functions which are symmetric and which are antisymmetric. We can always find them. No matter dependency, independency, here also we got symmetric wave function. The only important condition is that the wave function, the potential must be symmetric. In that, wave function now can be either symmetric or antisymmetric. We can always find them. So if they were dependent, then in independent case, if a is 1 symmetric, a is minus 1 antisymmetric. If this is independent, then even though these two are independent, there can be a function which you can express as linear combination of them. Now that function is symmetric wave function. That function is even function. Similarly, we can find an odd function also. Take 2b case. People, if alpha is 1 and beta is minus 1. Okay, what happens then? Then f of x, alpha psi of x, so that's 1 psi of x, and beta psi of minus x, that's minus 1 psi of minus x. Okay, so we have got psi of x minus psi of minus x. So this is f of x. Okay, now replace x with minus x. Replace x with minus x. So what do we have? F of minus x. What do we have? X ki jagah we have got minus x, and minus x ki jagah we have got x. Okay, take minus common. So this becomes minus psi of minus x plus psi of x. I've just taken minus property. If you open the brackets, minus minus is anyway plus, and minus plus is anyway minus. Okay, let's write the positive term first. I'm writing positive term first, and then I'm writing the negative term. But who is psi of x minus psi of minus x? Psi of x minus psi of minus x is f of x, people. You have got f of minus x is negative of f of x. This is anti-symmetric wave function. Potential must be symmetric. As far as potential is symmetric wave function, you can always get, you can find a wave function which is symmetric. You can find a wave function which is anti-symmetric. Doesn't matter, dependent or independent. Doesn't matter. I hope this is understood. Tell me if not.
So the crux is that if potential is symmetric, the corresponding wave function is anti-symmetric or symmetric, or
any combination, anything related to that also. I will create a flowchart. Wait.
Yes, sir.
Then people, let me write in. Okay, so basically, as far as potential is symmetric, okay, first thing that we discovered is the wave function corresponding to that psi of x and psi of minus x share same eigenvalue. That's the first important. They share same eigenvalue. Okay, but that does not necessarily mean that they are independent. That does not necessarily mean they are dependent. It could be anything. So now we have got two cases. One case where psi of x and psi of minus x are linearly dependent, and one case where psi of x and psi of minus x are linearly independent. If they are linearly dependent, then you can say that psi of x is basically a times psi of minus x, or you can say psi of minus x is a times psi of x, whatever. Okay, I will write it this way: psi of minus x. Let's say it is a times psi of x. And if they are linearly independent, then we define a wave function here, f of x, which is linear combination of them. Okay. Now in this we get a case where if a is 1, we get symmetric wave function. If a is minus 1, we get anti-symmetric wave function. And in this we get if alpha is 1, beta is 1, we get symmetric wave function. And if alpha is 1 and beta is minus 1, we get anti-symmetric wave function. I hope the whole flowchart helps you to understand this nicely, beautifully. The point is, this must be symmetric. You will get symmetric and asymmetric, symmetric and asymmetric, no matter what. Chalo, copy. Okay. Tell me if you have any questions. Don't hesitate, please.
So can you explain how this symmetric or anti-symmetric wave function will affect the state of the system or the system?
State of the system or the system. So I don't understand the question exactly, but I think you're trying to ask that how wave function, like if it is symmetric, then what will happen, and if it is anti-symmetric, then what will happen?
Yes, sir.
Well, instead of expecting a node like maximum intensity somewhere, you may end up getting minimum intensity, and instead of getting minimum intensity somewhere, you end up getting maximum intensity. It's about prediction. So for example, let's talk about sin x. Sin x is odd function now, but if you talk about cos x is even function. So sin x is symmetric, anti-symmetric wave function because it is odd, and cos, which is even, this is symmetric wave function. Okay. So the point is, if you plot a sin x graph, it looks like this. But if you plot a cos x graph, it looks like this. So in case of sin x, at let's say t/4, you will get maximum. But in case of cos x, at t/4, you get zero intensity. So if it's symmetric or anti-symmetric, that can help you to predict at which point the probability of finding the particle could be maximum, at which point the probability of finding the particle becomes zero. It helps you to predict things more nicely. Okay.
Okay.
No problem. Others, let me try writing copy. Writing, no? Okay.
Done, sir.
But he said writing or done?
Then
Okay, done. अच्छा wait, हाँ, okay,
आराम से देखो.
I'm just thinking, since the COVID cases are so massively increasing, just by any chance, if suppose you are given a choice whether you want to appear for exam in Feb, suppose, what would you do? Will you want to give, if you are given a choice, you can give it in Feb, you can also give it later. Suppose they decide that, because now it's likely also people, cases are increasing massively, exam might just get postponed, So what would you want if students are given a choice? Now or later?
Later.
Later में भी अच्छा, क्योंकि और
Preparation का time बचेगा.
और टेस्ट दे देंगे और भी अच्छा प्रिपरेशन करेंगे.
ठीक है. But at the same time, you need to remember that at the same time, everybody will get same amount of time. It's not only you. Then you need to trust yourself that you will be more effective in that break period. People think that if you get more vacation, more break, will be able to study more. But at the same time, everybody will study more. Now it depends on the sincerity of the student. If you think you are sincere enough, if you'll be literally utilizing the best of your time and you can increase your score, everybody's score is going to increase if you get a break time. But then how much can your score increase? Because somebody's score is going to increase, somebody's might just decrease. So that will depend on your effectiveness. Okay. So it's always a tentative option to postpone the exam. But at the same time, remember, most of you are maybe in your final year, some of you are repeaters, some of you are in your second year. But since many students who are in the final year who will also be giving exam, even now they will get a good amount of time to prepare. So you have to compete with them too, nicely. So that way, what I think, if you think you have prepared sufficiently, best is give it right away. But yes, provided you make again the most out of the remaining period you have. Sure. Next, proceeding ahead. So people, these were the theorems I wanted. That's it. And now we can start with the heart of the chapter, starting with potentials. So first, please give heading free particle without any potential. Please give heading free particle. So where potential does not exist whatsoever, basically it's zero from minus infinity to infinity throughout. From minus infinity to infinity, it's zero. Okay. Sure. So what is the
potential acting on that particle is zero.
Zero.
All
the points, on the points. There is no boundary condition at all. Okay. So in that case, what is our Schrodinger equation, people? We have learned Schrodinger equation. I've given you two equations, whatever you prefer to by heart. First equation was minus x square upon 2m d square upon dx square plus b into psi is e psi. This is fine. And then if you just rearrange all of this, then we end up getting d square psi upon dx square plus e minus b. No. Plus e minus b, no? Or this is, no, there's a minus symbol. Plus e minus b psi, this is 0. Can you just check? Somebody? 0.
Sir, 2m square छोड़ दिया.
2m square.
2m upon x square, yes. 2m upon x square, right? E minus b side, this is 0. Now it's fine. So the point, I will suggest you to by heart this equation is time series, because otherwise every time you have to use this one. Okay. So after this small manipulation, I will do the manipulation once again for last time. Next time onwards, you have to remember that equation directly. Okay. So we can just open the brackets. Minus x square upon 2m d square psi upon dx square plus b psi. This is e psi. Throw b psi on that side. So minus x square upon 2m d square psi upon dx square. This is e psi minus b psi. So that's e minus b into psi. Throw this constant on that side. So we have got d square psi upon dx square. This is equal to, now minus x square upon 2m goes on that side. That's minus 2m upon x square. Okay. Into e minus b psi, and we end up getting d square psi upon dx square plus 2m upon x square into e minus b psi. This is 0. Every time you have to do the simplification, so why not by heart this directly? Henceforth, I'll be using this. Okay. What are the copy? Henceforth, I'll be using this directly. Okay. This is our time independent Schrodinger equation.
Yes, sir.
Now let's substitute the respective conditions. So they have given you that potential is 0, people. So I can say that d square psi upon dx square plus 2m upon x square e minus 0 into psi. This is 0. So I have got d square psi upon dx square plus 2me upon x square into psi. This is 0. Now after this, you write something called as let in quantum mechanics in physics, and you say let k square is 2me upon x square. But again, textbooks don't explain. So why k square? I've also told you this before also. Like in oscillations also you do this, where you just write omega square is k by m. I have told you this, but again, I haven't given you the answer that why do you write omega square is k by m. But I told you this.
No, you have told us, but not the reason.
Not the reason. Okay, so everything has a
I
reason.
think the dimensions.
Yes, it is dimension. That's correct. That is it. It is dimensions. Omega, you define omega as angular frequency. No? Angular frequency is angular, like when you write 2 pi f or you write 2 pi by time period. 2 pi does not have any dimension. So omega has time, like the dimension of this would be 1 upon t1, or you can say this is t minus 1. The thing is, if you calculate the dimension on RHS, then the dimension comes out to be t minus 2. So that's it. What do we do? Omega square would be t minus 2. Dimensionally, they become equal. And hence we don't write omega, we don't write omega 2, we don't write root omega. It's simply because that dimensions on the left and the dimensions on the right match equal. They match completely. Okay? That's the first thing. That's obvious. That's logical guess. Good. Okay? You can calculate dimension of P and dimension of gamma. The dimensions will match. However, here there is more than dimension. It's not just the dimension. Dimensions will match, but it's more than dimension. Let me tell you what. So K is our regular K. What is K? K is propagation constant. It's not something random constant actually. K is our propagation constant. Do you remember we had learned while learning low velocity and phase velocity that momentum was expect K and energy was expect omega? We had learned this during
Yes.
and phase. Okay. If you don't recall, you remember momentum is h by lambda d log these. You just have to multiply and divide by 2 pi. So this becomes h upon 2 pi and this becomes lambda upon 2 pi. Okay. H upon 2 pi is h squared. Then you have 2 pi by lambda. 2 pi by lambda is K. So P is expected. Okay. You don't have to write this again and again, but since I've written this, I'll keep it. Anyway, so this is just, you directly remember P is expected first of all. Throw this h squared on that side. No? What do you have? H squared square, K square. This is 2me. Okay. H squared K, the whole square. This is 2me. H squared K is momentum, people. Momentum square. This is 2me. Momentum square upon 2m. This is E. What is momentum square upon 2m?
Energy.
Energy. But how? Obviously, you might think, but so that's kinetic energy now, and this is total energy. But people, potential is 0. I know. Potential is 0, so kinetic will be equal to total. Okay, kinetic will be equal to total. Have realization. For those who have learned this throughout your BSc, I hope you got the reason today. Make a note.
So can you please repeat the realization?
Repeat the process.
Realization. I mean, I got that P square by 2m is kinetic energy equals to total energy.
So energy is, so basically this is correct, right? Energy and kinetic energy. Because potential is 0 now.
Yes, so the total energy will be kinetic energy of the particle.
Kinetic is equal over. So since this is correct, it means 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 this is correct. So the point
Okay, so
is
you're
why?
going backwards.
Yes, that why K square is 2me upon x square. Why not K? Why not K2? Why not something else? Why only K square? It has a very complete logical reason. Okay.
Sir, please go to the last page once.
Okay.
Okay, sir.
By the way, right side and everything in red is not a part of the derivation method. Right now, we just want to write let K square is 2me upon x square. It is just I wanted you to understand that why do you write K square? Why not something else? Why not K to K? Or why only K square? There is a complete logic behind it. Any questions, anyone, anywhere?
No,
Please
it's
ask.
clear.
Sure. So let's substitute. I hope you're confident. Let me finish writing. Okay, here we go. So what do we have? D square psi upon dx square plus K square into psi. This is 0. This term is K square now. This term is K square. Okay. Now differential equation. So people, you can write D square upon dx square as capital D square. You write D by dx as first derivative. You write the second derivative as D square, and similarly you can keep on defining. Okay. So D square psi plus K square psi. This is 0. Then you take psi common. So D square plus K square is 0. And now this gives you solution. This gives you solution. Okay. So how do you start, people? You will first say, see, can wave function be 0? Wave function cannot be 0. So it means this term must be 0. So you see that D square plus K square is 0. It means D square must be minus of K square. It means D is plus or minus under root of minus K square. It means D is plus or minus, I can write K square into under root minus 1. Or I can say D is plus or minus K under root minus 1 is I. So we have got complex D, we have got complex values here. And then you know what to do after this. Complementary functions, people. You must have done 3 cases.
Hospital.
You must have done 3 cases: real and unequal, real and equal, and complex. I think I'll go through the cases because I require all the cases for quantum. I'll just go through all the cases.
Yes, sir.
Okay, so others writing better.
Done.
Let's take a small diversion here. Let's learn some mathematics because I require all the cases people throughout the quantum. Okay? So suppose whenever you have derivative, second derivative, I'm taking only quadratic cases because that is all that I require. D square y upon dx square. Okay. Plus suppose a into dy by dx plus b into y. This is c. If you are thinking, but sir, what if this also has a constant c and I divide that c now? Divide that c. Okay. So that way you get a and b. So I don't want any constant whatsoever. Okay. So what if you have a constant here, you divide that constant throughout, and you will still get a new constant here and a new constant b. So if you have something like this, what you do first, d square y plus a d y plus b y. This is 0. Correct. D square is second derivative, d is first derivative, and your coefficient is coefficient. Okay. Tell me if you have any confusions, don't hesitate. Take y common. So d square plus ad plus b. I can take y common. This is 0. Y cannot be 0. It means d square plus ad plus b. This is 0. Now this is quadratic equation. Okay. So here I will have 2 roots. Now depending upon the 2 roots, what we have is we have solutions. Right on this first. Depending upon the 2 roots, we have solutions. D square is second derivative, d is first derivative. A are written as it is, b are written as it is. Done?
Yes, sir.
Okay. So case 1. If both the roots are real and unequal, then people, your solution y is written as c1 e raised to m1 x plus c2 e raised to m2 x. But m1 and m1 are the roots, so both the roots are m1 and m2 basically. So whatever roots you find after solving now, because when you solve this, you'll have 2 values people. So those values, first value is m1, second value is m2. So when you have 2 roots, so one is m1, other is m2. So if the roots are real and unequal, then this is how you write the solution. C1 and C2 are constants. We will find constant using boundary conditions in quantum physics. So suppose if you get m1 is 3, suppose you get m2 is minus 2. They are real now, first of all, and they are unequal. Since they are real and unequal, your solution is y is c1 e raised to m1 x plus c2 e raised to m2 x. But we have to find c1 c2 using boundary conditions in quantum. Let me know if you have any questions. So just because we are discussing this, if you had a third root, okay, in that case you write c3 raised to mcx. If you have 4, then c4 raised to m4x, and you go on. Next, shall we? Case 2. Okay, case 2. If both the roots are real and equal, okay. So suppose m1 and m2 are equal, but at the same time they are real. Something like right now I'm writing m. Okay, I'm writing m. So then you write y as c1 plus c2x e raised to mx. This is important. C1 plus C2x e raised to mx. So for example, if you find out m1 is m2, both are equal and both are minus 3, real and equal. So your solution y will be C1 plus C2x e raised to minus 3x. Okay. And just saying, if you had a third root, we don't have third root in quantum mechanics, but in this mathematical physics, if you had third, then what do you write? C1 plus C2x plus C3x squared e raised to mx. If you had fourth, then C4x cubed, fifth equal, then C5x 4, and it goes on. It goes on in that case. If you have third equal root, then C3x squared, fourth equal root, then C4x squared, x cubed, and it goes on. Okay. We don't need third root, however.
Yes, sir.
In case 3, if the roots are complex pairs, okay. So basically, you end up getting, when you write a d, so you end up getting d is plus or minus. Okay. Basically, you'll have something like this eventually. Alpha plus or minus beta I, something like this. So basically, one is alpha plus beta I, other is alpha minus beta I. One is alpha plus beta I, another is alpha minus beta I. Okay. So this is the first root. This is the second root. This is known as complex pair. If you have something like this, then y is written as e raised to alpha x into c1 cos beta x plus c2 sin beta x. Okay. Example. Suppose you end up getting the d is minus 1 plus or minus 3i. This is a complex pair. First one is minus 1 plus 3i, other is minus 1 minus 3i. In that case, solution is e raised to alpha x. You can compare alpha plus or minus beta I. Alpha is minus 1, beta is 3. So e raised to alpha x, 3 raised to minus 1x. Okay. C1 cos beta x. So C1 cos 3x plus C2 sin beta x. So C2 sin 3x. Okay. I need you to do one thing here. When you write if the roots are complex pairs, this and this, okay. Say this is A, write A here, and this is the example of A. This is the example of A. Copy it, okay? And then write or. You will have option. Either you can use this, which we will use all the time. Mostly we go for this, or B. Or you can use B case also. We'll learn this B case later for a reason. Just leave 3-4 lines for a second. Okay? So just like we have written this, there is another method which we can use in some specific cases. Okay, that I will teach you later, and I will also give you an example later. So whatever are the 3-4 lines here, same just like or, and right, just leave 3-4 lines. When the time comes, I'll come back to this page. Okay? Just leave 3-4 lines.
Okay, sir.
Okay. So you have the choice to use either of them. So I require these 3 throughout our quantum. Okay, sure. So going back to the question, diversion is done. So people, this is a complex pair. We have got D is plus or minus Ti. So I can write this as 0 plus or minus Ti now. Okay, it means this is alpha plus or minus beta I. Alpha is 0, beta is k. So what's our solution, people? Y, instead of y you have psi. Okay, instead of y you have psi e raised to alpha x into c1 cos beta x plus c2 sin beta x. So what do we have? Psi is e raised to 0 x c1 cos beta, which is kx, plus c2 sin beta, which is kx. Anything raised to 0 is 1. So our wave function is, people, c1 cos kx plus c2 sin kx. I hope you are with me. That's the wave function of a free particle. Done. That's the wave function of a free particle, people.
This is the what is this? The wave equation for the free particle.
Free particle, yes. And we don't have any information on C1, C2 because we don't have any boundary conditions here. By heart, this is the wave function of a free particle. Any questions? Anyone? Anywhere?
Sir,
बोलो.
sir, beta कभी negative होगा क्या? ना नहीं होगा कभी भी.
No, नहीं होगा because plus minus or minus plus. It's always in pair, no? So beta won't be negative.
कभी भी नहीं होगा.
नहीं, never.
Okay, sir.
चलो, done ये.
Yes.
Proceed ahead. So free particle cases, that's it. And you can write we don't have information on C1, C2 because here there is no boundary available. It's free throughout. How can we even have a boundary condition? We cannot have that. So this is it. This is the wave function of a free particle. Now let's take the next case, which is popularly known as infinite square well. Infinite square well. Actually, in infinite also, people, there are two kinds. One is unsymmetric, other is symmetric. So I'm taking infinite square well. In that, I'm taking unsymmetric square well. Unsymmetric one. Okay. And this is popularly known as people 1D box. Okay. Let's start with 1D box. So how do we define 1D box? So box basically means particle must be within something and it cannot exist beyond that. Now you have a boundary. That's it. So suppose this is your v of x. Let's say this is your x-axis. X-axis. Let's say this is v of x. Okay. People, just have a look for a second. Don't write. A symmetric would be something like this. This is known as symmetric because it's equal on left side, equal on right side. But we are going to draw it like this. So everything is on right side. There's nothing on left side. We are taking unsymmetric right now. We will take symmetric eventually. 1D box is popularly unsymmetric only. We don't define 1D box for symmetric. Okay. So we are taking a box like this. So this is not symmetric because on left side you have nothing. On right side you have the box. A symmetric would be when it is equally divided. Okay. So people in 1D box
With respect to potential.
with respect to potential axis, with respect to y-axis. So this would be, if you want, you can draw this above margin, above, just in small diagram. Just draw this above margin. This is symmetric potential. Write it above margin. This is symmetric potential. Symmetric box. So on y-axis, left side and right side, it is dividing equal. Okay. So v of x and v of minus x are equal basically here. V of x and v of minus x are equal. Symmetric potential, people on left and right side. Okay. But we are not interested in this right now. We are taking the unsymmetric potential. Okay. So this one, if you want, you can also draw this one above margin temporary. This is unsymmetric because the whole box is on the right side. On left side, you have nothing. This is unsymmetric. Okay. So what is the meaning of infinite? It means potential is infinite. That's it. So you can draw a box. We can draw a box here. But the margins of the box, people, they will end up having infinite potential. So it goes until infinity. So v of x is infinity. V of x is infinity, people. You can write it in above if you want. Here it reaches infinity, it will go on. Okay. Here also it will keep on going. V of x will go until infinity. But between them, v of x is 0. Between them, potential is 0. Okay. So here x equals to 0. This is origin. This is origin. And the box has a length. Let's say x equals to L. Okay. So this is 1D box of length L, people. 1D box of length L. Okay. This is 1D box of length L.
Sir, the potential difference between the two sides is 0 या फिर उसके अंदर का region
No.
potential?
Under the potential is 0. Completely 0. Potential is only 0. 0 potential. Free particle.
At x-axis.
Along x-axis. It's completely along x-axis. Yes. So it's infinite, 0, infinite. So basically, if you want to write, you can write it this way: that v of x is infinity for x less than 0. V of x is 0 for x greater than 0, but between L, and v of x becomes again infinity if it is greater than 0. But between it is 0. It is infinity on left hand side when x is less than 0. It is infinity on right hand side when it is greater than L, but it is 0 between 0 and L. Okay.
0 L per infinity.
Yes. So if you want, you can put equality here.
Yes, sir, equal.
You can put equality here because 0 and L wave function vanishes. So we can also discuss the wave function. We learned this in theorem number 2. If potential becomes infinite, wave function vanishes. So if you want to define wave function is not defined. Okay, it is not defined. Or you write 0, whatever you want to, for x less than or equals to 0, and wave function is not defined, or 0, whatever you want to write, for x greater than or equals to 0. Wave function, you can define wave function, let's say psi of x or psi, whatever, that will be between L and 0. This is L by the way. Okay. So less than 0 wave function is not defined, greater than L wave function is not defined, between only it is defined. Only in between it is defined.
Yes, sir.
Okay, sure. So since it is now we have boundary conditions basically, so you can simply say that at the boundaries wave function becomes 0. You write not defined or 0, like that's also fine, doesn't matter. But the point is it cannot exist, it vanishes. Even if it would exist at 0.1, at 0 it becomes 0 basically. So we have boundary conditions, people. Boundary conditions is simple. At x equals to 0, wave function becomes 0, and at x equals to L, wave function becomes 0. I hope you are also understanding the boundary conditions now. X equals to 0, wave function is 0, and x equals to L, wave function is 0. It vanishes. Theorem number 2, people. Okay. Chalo. Next.
सर ये क्या लिखा BC में?
Boundary conditions.
Okay.
And conditions. Okay. Next. So our region of interest is basically the between region people now. Okay. So I can say the wave function is free. The wave function is free between 0 and L. Okay. And people, but for a free particle, we already know the answer. Okay. We already know the answer. Otherwise, we would have derived this, honestly. But we already know the answer for a free particle. What is the wave function? C1 cos beta x plus C2 sin beta x. And this time we can find C1 C2 because we have boundary conditions. Okay. So let's find them. So this is psi of x people. And now we can use boundary conditions to find C1 and C2. So let's use the first condition. People, when psi of x is 0, when x is 0, then psi of x is 0, when x is 0, substitute. So 0 is equal to C1 cos 0 plus C2 sin 0. So 0 is C1 into cos 0 is 1 plus C2 into sin 0 is 0. So we have what 0 is C1 plus 0, or I can say 0 is C1. People, C1 is 0. C1 is a constant. Even though you are using a boundary condition to find the constant, once a constant, always a constant people. Okay. Like suppose if you take a graph, if you calculate constant for this point, and it means it's valid throughout because it's a constant. So since C1 is 0 here, it's 0 throughout. So resubstitute it here, your wave function reduces people. Now wave function reduces to C1 is always 0. Okay. Just C2 sin beta. Just C2 sin beta. Achha, beta was k by the way. You can always argue it. Beta was k. We had C1 cos kx and C2 sin kx. Huh? Attention though, Ray. Okay.
Okay, sir.
So what do you mean by psi x is free between 0 and L?
I mean wave function particle is free. Forget psi x particle.
Okay, particle is free between
0 and L. It is not. V of x is 0. No potential. No potential. Free particle. How confused?
नहीं सर अभी सेंस बन रहा है आप क्यों यूज कर रहे फ्री पार्टिकल का
हाँ
क्योंकि मैं भी कंफ्यूज हो गया था कि क्या बोल रहा
yes understood now हाँ so particle is free between 0 and L. So for a free particle you already know the wave function. Okay, but earlier we did not have a boundary condition. Now we have a boundary condition. Okay, I hope you are understanding that. See, I don't mind repeating. I told you that. You can always ask me, sir, please repeat, please explain. Please, very effective. Okay, hello, done. Have copied this, shall we?
Yes, sir.
Okay, so now we want to find C2. Okay, so how do we find C2 then? Let's use second boundary condition. So wave function is 0 again. Wave function is again 0 when your value of x is L. Okay, so what am I writing? Hang on. So wave function is 0 when x is L. So let's use this. So we have a function psi of x is sin 2x. It's already reduced. Huh? Psi of x is C2 sin kx. Okay, so 0 is equal to C2 sin k into L. Okay,
Yes, sir.
so I can say 0 is sin kl. Constant cannot be 0, otherwise wave function will vanish. We know that wave function cannot vanish. First of all, understand here C2 cannot be 0. That is for sure. Because if C2 will become 0, wave function vanishes in between region also. That's impossible. Wave function exists. Particle exists in between. We have said already. So C2 cannot be 0. Since C2 cannot be 0, it means sin kl can be 0. Okay. Now what are the possible values when sin kl becomes 0? You can write it out. C2 cannot be 0. Obviously, C2 cannot be 0.
So why, sir, please repeat? Why C2 cannot be
You see, C1 is already 0 now. Okay, so C1 is already 0. If C2 will also become 0, then wave function will become 0. You see, particle doesn't exist in between region also, but it exists now.
Okay,
So, so C2 cannot be 0 now. Okay, so I can say that sin kl is 0. So what are the values where sin becomes 0? Sin 0 is 0. Sin pi is 0. Yes, sin 2 pi is 0, and it goes on. Sin kl. But specifically, I written it this way. Listen, people. Out of this, I have to ignore this value. Again, why? For that, I have to connect this later to Heisenberg's uncertainty principle. I will come back to this. If you want, you can put a question mark right now. I will come back to this once we complete the derivation. Okay? So we cannot have this value. Here, all the values are allowed except this value. I repeat, all the values are allowed except the first value. If you want, you can write it neatly. Copy this and write down. All the values inside the sign are allowed except 0. Why 0 is not allowed? I will teach you that eventually. All the values are allowed except 0.
Okay, 0 पे boundary नहीं होगा शायद.
No, it's not that. If that becomes 0, energy can become 0. It means you are saying ground state energy actually becomes 0. It means you are defining energy with accuracy. That's impossible. There should be uncertainty involved. It's related to Heisenberg's uncertainty. I will come back to that. Have patience. Okay? It's interesting. But okay. So just write out the side. All the values are allowed except 0. Okay. So 1 pi, 2 pi, 3 pi, 2 pi, all the pi's are allowed. So you can write sin n pi. You can write sin n pi is sin kl. But mention it very clearly, and it's not whole number people. N must be natural numbers. Basically, you know what will happen eventually? These are natural numbers, but eventually this will become principal quantum numbers also. Right now, these are just normal numbers. Eventually, you will realize that energy is related to them. You know, just like a hydrogen atom is inversely proportional to n square. Here also, it will be proportional to n square, directly proportional to n square, and they will clear over quantum numbers people. And quantum numbers does not have 0 value. Okay. But anyway, we'll come to this right on the side. N takes all the value except 0. 1, 2, 3 goes on. Okay. So sin gets cancelled. What do we have? N pi is kl. Okay. So what do we have, people? N pi by l is k. We have what n pi by l is k. Make a note and give this equation 2, 3, 4, star mark, whatever. N pi by l is k.
Yes, sir.
Okay. So substitute this back to this equation, people. Say this is equation 1, C2 sin kx, and say this is equation 2. C2 sin kx for the equation, say that is 1, people. C2 sin kx, that's 1. And this n pi by l is k, that's 2. Put 2 in 1, what do we have? Okay. We have psi of x is C2 sin kx now. But what is k? This is C2 sin k is people n pi by l, n pi x by l. You remember I had taken a question purposely for this stage where we were finding normalization constant and we ended up finding so how do we find C2? If you were thinking as of now, how do we find C2? Normalization condition, because particle 100% exists between 0 to L. It cannot exist beyond that. It exists between them. So using normalization condition, we find C2, and that we have already did. I have reduced half of my job. Okay. So you can write now that we can find C2. Okay. We can find C2 using normalization condition. Using normalization condition. Okay. Smart work done already. Okay. So what is normalization condition? Integration of psi star psi dx. It is 100% 1 between 0 to L. It has to exist between. You can write because it is bounded. Beyond this, it cannot exist. You can write all space first. You don't want to write all space, but our all space is not minus infinity to infinity to the side. This is your Max Born theory, by the way. You can write Max Born theory. But this becomes normalization condition or whatever. This becomes 0 to L because all space is not all space for us. It is bounded. Wave function must exist between them. all space is 0 to L for us. Okay, and solved this already. We have solved this already. Using this, we had found out C2 was under root 2 pi L. And with this, we get the 1D box ka wave function. I hope you understood this neatly.
So what is Max Born theory? All space or 0 to L?
All space, all space. 0 to L2 is the 1D box limitation. That particle exists between 0 to L. Here it cannot exist, it vanishes, here it vanishes. It exists between 0 to L only. It cannot exist from minus infinity to infinity. Like if you start from minus infinity to infinity, you have to divide it in 3 parts. Here to here, then here to here, and then here to here. Here it becomes 0, here it exists, here it becomes 0. Clear?
Yes, sir.
Okay. So our final answer, psi of x people of 1D box comes out to be,
So it's
right? Take your time.
Yes, sir, please carry on.
Sure. So psi of x is root of 2 by L sine n by x by L people. That's our wave function. You can define psi n.
Wave function of a free particle inside a 1D box.
Yes. Wave function of a particle inside a 1D box. Like 1D box.
Free.
Yes. So wave function of a particle inside a 1D box.
So 1D box means 0 to L, no?
0 to L and its infinity on other sides.
Okay.
This is wave function of particle in 1D box. Right. Okay. Remember, you can have psi 1, psi 2. Like if you want, you can write psi n here. So because if n changes, wave function changes. Nothing changes in this one. Everything else is constant. So it changes with n actually. Okay. So psi 1 would be under root 2 by L sine 1 by x by L. Okay. Psi 2 would be under root 2 by L sine 2 by x by L. And it goes on.
Each of these psi 1, psi 2 are eigenvectors.
Eigenvectors, they are linearly independent. All of them are linearly independent. These are eigenvectors because they all will have a corresponding energy eigenvalue, individual eigenvalue. These are eigenvectors. They all will have individual eigenvalue. They all will have individual energy eigenvalue. They are linearly independent eigenvectors. People. Okay. And let's learn the energy people. Energy also we had used in the numerical, but how that energy comes, let's understand. So I hope you have covered this up.
Yes,
So we have already defined k square was 2m upon x square. We had defined this as let if you remember. But we have already learned k is also n pi by L. K is also n pi by L equal to. What do we have? N square pi square. I hope remember this was let people and this was that star part. This was the star part I had written and this was the let part I had written. I'm just equating them. Okay. So k square is n square pi square upon L square. This is 2me upon x square. So we got the answer people. N square pi square x square upon 2ml square. This is energy E. Now here everything is constant except n. Energy is also a function of n people. This is the energy eigenvalue. This is the energy eigenvalue. E1 would be pi square x square upon 2ml square. Okay. E2 would be pi square 2 pi square x square upon E2 if I'm writing and 2 square 2 square is 4 actually. 4 pi square x square upon 2ml square. If you're writing E3, then it is 9 pi square x square upon 2ml square. So this is En. Energy eigenvalue En. Here also you can write wave function psi n. Psi n which depends on n and En which depends on n. One thing right now, please write in capitals above marginal wherever. People in hydrogen atom, energy was inversely proportional to n square. But in 1D box, it is directly proportional to n square. This is a very big mess which students create. I don't know what they think. In 1D box also they end up using this. Here it is directly proportional to n square. In hydrogen, which was minus 7.6 upon n square. That was different people. This was in hydrogen atom. Yes, there was Z dependency also. I'm not writing Z dependency. I'm just trying to make you understand the relations for quantum numbers people. And this is 1D box. So in exam, if I ask you ratio problem, be very careful. A very common mistake with students. So in 1D box, they end up writing inversely proportional to n square because hydrogen is their favorite. Every time they see minus 13.6 upon n square, they think it's inversely proportional to n square. Now, in 1D is directly proportional to n square. Okay?
Yes, sir.
Good. So we have found out 1D box wave function and 1D box energy eigenvalue respectively. Okay. Understand? Psi 1 has energy E1 because for both of them n is 1 now. Here you substituted n1. Here also you substituted n was 1 people. Psi 2 has energy E2 because here you substituted n is 2 and here also you substituted 2 square which becomes 4. Okay. So you can simply write that psi n for wave function psi n which is root of 2 by L sine n by x by L wave function has eigenvalue as energy value En which is n square pi square h square upon 2ml square. So by the way, many students and many books don't prefer to write h square. They write answers in h. So in that case, you have to just make small manipulation here to get rid of h square. So n square pi square upon 2ml square. What is h square? H upon 2 pi. The whole square. So this will become n square pi square upon 2ml square. This is h square upon 4 pi square. People pi square is cancelled. In that case, energy becomes n square h square upon 8ml square. That's it. Both of them are correct. Both of them are correct. This is in terms of h square and this is in terms of h. Actually, there was one of the MSQ in one of the papers, not in JAM, but basically one of the papers that basically I had said earlier. So where I had given both the options, where En was n square pi square h square upon 2ml square, and there was a D option where En was n square h square upon 8ml square. Students marked A, but they did not mark B. Both of them are correct now, but one is in terms of h square, other is in terms of h. Both of them are correct. Okay. Clear, everyone?
Yes, sir.
Okay. So actually, time is about to be dead, but I can explain in just 1 minute that why n equals to 0 was ignored. Let's quickly understand. People, what will happen if n becomes 0, energy becomes 0 first of all. As you can clearly see. Okay. So if n is 0, energy is 0. Energy is kinetic plus potential, but potential is anyway 0, it's free particle. It means kinetic is 0 because potential is anyway 0, free particle. If kinetic is 0, then p square upon 2m is 0, but mass cannot be 0, and mass cannot be infinite. It means p square is 0. It means momentum is 0. It means error in momentum is 0. If error in momentum is 0, then error in position is infinite, which is wrong. Because the maximum possible error you can have is L people. In 1D box, maximum possible error you can have is L0 to L. That's it. We cannot have infinite as the error people. And hence, n equals to 0 is prohibited because it violates Heisenberg's uncertainty principle. N equals to 0 is prohibited because it violates.
So p equals to 0 and then delta p equals to 0. How?
If momentum is 0, then every momentum is 0. No?
Derivative. So the uncertainty.
You have defined it precisely. Momentum is 0. There is no error. definition. Momentum is zero. If I tell you momentum is even 3, you have defined it. If
Okay.
definition, error is zero. Basically, if it's constant, then derivative is anyway zero. Change is zero. Anyway, either way you value. Okay. So n is equal to 0 is prohibited as it violates Heisenberg's uncertainty principle. Clear? Thank you so much, everyone. We'll meet tomorrow. We'll continue with 1D box. We'll take many problems, and we'll also take 2D, 3D tomorrow. Emily, thank you.
सर डेल्टा x इक्वल टू l क्यों है मतलब अराउंड कुछ
हाँ, क्योंकि 1D box में particle has to exist between 0 to alpha.
Yes, sir.
How can it be infinity? So maximum error you can say is L. Like you have predicted it is 0, and maximum it can exist is at L.
ओके ओके मतलब ज्यादा होगा भी तो l होगा
हाँ, max to max होगा L. Infinite is not even an option. हाँ.
ओके हाँ थैंक यू
ठीक है, so you just write, I edit here. Delta x max is L is maximum possible error is L. Okay. चलो, Emily, thank you.
Thank you, sir.
No problem.
Thank you, sir.
No problem.
Thank you, sir.
No problem. Shall I end the session? People, let me know if anybody's writing. Should I?
Yes, sir.
See you tomorrow.